Hey, how's it going? Oh, well, my mic's all the way over here. Uh-oh, you guys can't hear anything. Let's try that again. Hello, AP Calculus students. Mr. Ford here with the first homework tutorial of Chapter 5. From this point forward, we're just going to be working at the best pace we possibly can to get to the end here. So this is 5.1.1. You can expect us to do one section every day. There are some things we're going to skip along the way, so pay attention to the order of things, and Google Classroom will have the assignments in them as we go. Anyway, let's jump into problem 5.5, which is a direct continuation of a problem that we're going to do today during class. I'm recording this during second hour. Spitwads part 2. Now, in part 1, I'm going to go ahead and just give you the equation. This is telling you the height of a spitwad over time, h of t. Now, that is a position function because it is a height function. And we should, just for the organization's sake of our lives here, we should right next to it write down the velocity function because that's just going to be the derivative. It's h prime of t, which in this case is 64 minus 32t. What you're going to notice is that pretty much every function that has to do with velocity or position on Earth, you know what, we might as well just do the acceleration function here too. It's going to have the same acceleration and therefore the same velocity because of the way gravity works. Acceleration on Earth is 32 feet per second, and so you're always going to see negative 16t squared in position and negative 32t in velocity because those are the antiderivatives of the original constant acceleration due to gravity of negative 32 feet per second. That's a thing that'll come up in a later question on this assignment. But so before we even do anything, we should get that information out in front. These are really good questions if you're struggling with the connection between position and velocity and acceleration. We're going to see a lot of that in Chapter 5, so you're going to get a lot of practice with that kind of stuff. How high is the spitwad after half a second is the first question. How high is a distance question. So we are asked in question A, what is h of 0.5? Essentially, we're going to do a lot of this on the calculator too. So I'm going to bring calculator cam up to the front. The second question is how fast is it traveling at that instant? So we also want to know v of 0.5. Those two things. So this is question A. We're just going to plug in the half a second time frame, 0.5. Let me get that cord out of here, my mouse cord. We're just going to plug that information right into the height function. So for the first part, 64 times 0.5 minus 16 times 0.5 squared is going to give us 28. That's the height. It's at 28 feet after 0.5 seconds. And the velocity at that time is 64 minus 0.5, minus 32 times 0.5. If I could use a calculator, that would be helpful. I don't need a calculator for that. That's 64 minus 16. It's 48 feet per second. That would be what's going on there. I'm pretty sure that is correct. 48 feet per second at that instant. That's how fast it's traveling. It's at 28 feet or inches. I don't know what this is. I can't remember oh, it is feet. Like that. That's it. So she's pretty good at spitwads if that's her target there. I'm checking. I got the answer key in front of me. That is correct. Okay, cool. I don't want to give you wrong answers for any of these problems. Next question, when is the spitwad 10 feet high? If we translate this, now again, this is a height function, but for question B, the question that we're answering is, when is h of t equal to 10? That's the question. We're not plugging 10 in. We don't know the time. We know where it is, height, so we're actually going to find out what t is. So for this, we're going to solve this equation, 64t minus 16t squared equals 10. That might be a tricky question to answer, so let's first of all arrange it like a quadratic equation. 16t squared plus 64t minus 10 equals 0. I suspect this does not have a whole number answer, so maybe the quadratic formula would be a good way to answer this. There are going to be two solutions, and I believe they'll both be positive, so the quadratic formula I think is probably the best way. Negative 64 plus and minus the square root of 16 squared. I guess it's negative 16, but it won't matter. Minus 4 times negative 16 times negative 10. We'll let the calculator do all of this work for us, all divided by 2 times negative 16. So we're going to let the calculator handle this work for us, but this is a question that we can answer relatively simple if we have at least a little bit of working knowledge of that formula. So on top, negative 64 plus the square root of negative 16 squared minus 4 times negative 16 times negative 10, all divided by 2 times negative 16. That will give us our first answer. Whoa, non-real answers. Get out of here. No way. What? Oh, sorry. It's 64 squared right there. My fault, fam. Yeah, negative b plus or minus square root of b squared. So that's 64. Let me go over here and change that really quick. That will give us a nice big number for 64 squared, which will ensure that the discriminant is positive. There is one of our answers that is 0.16288. But the other answer is the same formula, only we change that to a subtraction. You could also do the same work that we're doing here by, you could just graph the parabola and then graph the line y equals 10 and see where it crosses. That would be another way to do it. 3.837. Those are the two solutions to this quadratic equation. So again, you could graph this and see where that horizontal line y equals 10 crosses it, but those are the two time frames where the spit wad is 10 feet above the ground. As far as v of t goes, what is its velocity at those times? This is going to be another calculator question. We're going to take the answer and plug it right in. But we're going to plug these answers in. Since these are the times that the spit wad is exact that height, the question is going to ask us what is the velocity at those times. We're going to find out what v of 0.16288 is, and we're also going to find out what v of 3.8371 is. And for that, we're just going to plug that right into our velocity function. This is a time to point out that you can cleverly use your calculator to do a lot of legwork for this problem. I'm just going to program into this equation our original height function and our velocity function right there. And I'm going to go ahead and turn off this the position function, because all I really care about right now is the velocity. I'm going to use the table function to do this. So I'm going to go into table settings, and I'm going to type in 0.16288. That'll start our table right there, and the velocity at that time is 58.788, which we have there. 58 point, yeah. That's the velocity feet per second at that time. And then the velocity of the other number was 3.8371. That one is, I believe, also, it's negative 58.788, which kind of makes sense because at those times, if you're thinking about this like a parabola, at those times, the curvature of the parabola will be the same, just one's positive and one's negative. So that kind of makes sense if you think about it a little bit. Okay, kind of boxing out my answers here. There's my answer for B. Again, you could pause that and just look at the work if you're kind of stuck on all the stuff we did there. Relatively straightforward. There's a lot of legwork to do, but the actual process is, what you need to do is pretty simple. For question C, as the spit wad is falling back towards Marisol, does it ever fall at a rate of 10 feet per second? So this question is asking us if v of t is ever equal to negative 10. And I say negative 10 because it's falling at a rate of 10 feet per second, and velocity cares about direction. So that's the question we need to solve here for question C. Does our velocity function ever equal negative 10? That's what we're going to solve. We could probably do this by hand because the velocity function is not particularly challenging to work with. It's 64 minus 32t equals negative 10. So negative 32t is going to equal negative 74 when you subtract the 64 over. If you divide by negative 32 on both sides, you're going to get a relatively simple answer. At least it can be kind of expressed as a fraction. 74 over 32, 2.3125. And that is a time. That's at what time the velocity is changing at that rate of negative 10 feet per second. And question D is going to ask us, how long does the spit wad take to reach its highest point, and how high does it go? And we're going to determine our answers both graphically and analytically. Let's do it analytically first, and then we'll take a look at the graph. This is question D. The reason why we're spending a lot of time on this first question for the homework is because it's a really important question. And I like that this video is going to be kind of long, but I kind of like it because this is a really important, like at the heart of everything we do in this class, everything we do in calculus this is a really big deal. So what we're looking for is what's the maximum? The maximum of h of t. To find it, there's a couple things you could do. You could take your original h of t function, which I think is 64. I gotta remember myself really quick here. 64t minus 16t squared. What we want to do, if you think about this as a parabola, which it is, let's draw a little quick graph of this. It's going to be a parabola. It's going to start at 0, 0, and it's going to go up, and it's going to come down. What we're looking for is that maximum point. Now, you could, I suppose, you can find the vertex by using vertex form of a parabola, but in calculus, what we're going to do is use the fact that at this maximum point, you have a horizontal tangent. In other words, the slope is equal to 0. So what we're going to do is we're going to take the derivative, v of t, which is the derivative, which is equal to 64 minus 16t, and we're going to make that equal to 0 and figure out when that happens. It's actually pretty simple to do. Negative 16t equals negative 64, and so t equals 64 over 16, which I think is a pretty solid 4? 64 over 16. Oh, 64 over 16. Yeah, pretty solid 4. Happens at 4 seconds. Right there. So, yes, the maximum occurs... oh, why does the book say 2 seconds? That doesn't seem to me to be right. The maximum occurs at 4 seconds. But doop. Let me think about this one. Did I do that right? Oh, I forgot. Sorry. Sorry, guys. I withdraw because I forgot to take the derivative correctly. It's 32t. Right there. That's going to change things considerably. 64 now equals 32t, and so t is equal to 2. Okay, that's better. I like that. Oh, I'm glad I keep the answers on one side so I can check myself if I'm wrong. Now, that is when the maximum happens. That is not what the maximum is. To figure out what the maximum is, we need to figure out what h of 2 is. So we'll just go on our calculator really quick and figure out what 64 times 2 minus 16 times 2 squared is, which I think it's going to be relatively simple to do. I'm not going to expand calculator cam. I'm just going to do the work right now. 16 times 2 squared, which is going to give us 64. And that is a feet because that is the actual location of where that is. So that is this point up here now we can say is the point 264 right there. Pretty cool. That's a really cool application of calculus. We didn't have to graph anything to figure that out. We just were able to do it with derivatives. On the calculator, by the way, you could, I'm going to turn my graph on again. And I'll change my window here. We care about probably 0 to 6 seconds, maybe 0 to 10. And then our maximum height looks like it's 64. So I'm going to go from 0 to 80 with a scale of 5. And you can see the graph. There's the graph of the position of the spit wad. And then the next graph coming through will be the speed of the spit wad, the velocity, which actually goes negative because the velocity goes down over time over there. Okay, that took about 13 minutes to get through that first question, but I kind of knew that going in that this one was going to be a little bit long. We'll be doing a lot of this stuff. We did a lot of stuff. If you're watching this after class, we did a lot of that same work in class anyway, so you could probably do that problem a lot faster. 5, 6, I really like, so we're going to do it. We have a bunch of information about p, some function p. We'll never know what p of x is, but we're going to sketch a possible graph of it by using this knowledge. The only point we know on this graph is that p of 0 is 0, so I'm going to go ahead and graph that. I'm also looking at all the other information. These are all derivatives, which means these are all slopes of our graphs at certain times. So I am going to go, and I notice that they go from 0 up to 6, so I'm only going to graph kind of the right side of the axis. I'm going to draw like this, kind of. Because I know that this graph has the point 0, 0 on it, because that's what this tells us right there. But everything else I know about it is a slope. I know that, for example, p prime of 0 is 1. So at this point, the slope is 1. So I'm just going to put a little dash on there, a little orange dash with the slope of 1, a 45-degree angle. And we're going to do that for all of these points, 2, 3, 4, and 5, and 6. We know the slope at 2, for example, is 0. So since it's increasing, I have to be up above the x-axis, but I'm going to put just a horizontal line there above 2. Because I know the slope has to have a 0 there, or a slope has to be a horizontal. At 3, the slope goes negative. So if somewhere above 3, I'm going to go ahead and put a negative 1. Kind of the same slope as that orange line, but with a downward 45 degrees. Now, p prime of 4 is negative 5, so it's going to be very, very, very steep. The graph doesn't have to go negative. We don't know where it is, but we do know that it's very steep. I'm going to put this down here. Negative 5 would look something like that, probably even steeper. And then p of 6, p prime of 6 is 0 again, so it's going to have to be down here because it's decreasing or so, but the graph doesn't have to be anywhere. All we know is what it's kind of doing. And from there, I can kind of just sketch the graph and, follow the curvature of those lines that I've drawn. The graph doesn't have to look like that. You can move it up and down basically anywhere. As long as it follows those slopes, that's what you're looking for. 5.7, the first derivative tells us the slope and the rate of change. What does the second derivative tell us about f prime? What does f double prime tell us about f prime? So there's a connection here, is that the derivative tells the slope and the rate of change of f. Now, the second derivative is the derivative of f prime. So the second derivative tells us the same information about f prime. And here's how I'd write this in 5.7a. I'd say that f double prime tells us the slope and rate of change of f prime. F double prime gives us the same information about f prime as f prime gives us about the original f, or the original function. However, there's another question here too, is that what does f double prime tell you about the original function? And we're going to put another sentence here. F double prime tells us the concavity of f. That's the connection that we got to have. So f double prime has the same relationship to f prime as f prime has to the original function, but when you're relating the second derivative to the original function, you're talking about concavity. So there is kind of a ladder of importance here. You have your f, you have your f prime, you have your f double prime. And these guys, you have the slope. And these guys, you have the slope. But when you're comparing the original function to f double prime, now you're talking about concavity. And you're talking about concavity of the original function, not of f prime. Chapter 5 and beyond is going to really lean into this big idea. We'll get to really explore that. We've seen it a few times. Certainly not our first time seeing that idea, but we're going to get to see it a lot coming forward. Question B is going to ask us to write equations for f prime and f double prime if f of x is that polynomial there. So let's get to work. F of x, the original function, is x to the third plus 3x squared minus 9x plus 2. So our derivative, f prime of x, just following the power rule, is 3x squared plus 6x minus 9. Notice how it dropped down a degree. That always happens. F double prime here in orange would then be 6x plus 6. Drop down another degree, which always happens. When you take derivatives, you go drop down a degree. If you integrate and go up antiderivatives, you'll go up a degree. There's question B. I like that answer quite a bit. Question C, is f getting steeper or less steep at x equals 1? When it comes to determining the steepness of the graph, we're talking about f prime. So C is really asking us, what is f prime of 1? Which is a really easy question to answer. I'm going to go highlight this question and then highlight this equation because they're going to ask the same question. F prime of 1 is going to be 3 plus 6 minus 9. Which is a really solid 0. So that's kind of a trick question. Is it getting steeper or less steep at x equals 1? It's neither. It's actually a horizontal tangent. It's staying exactly the same. I'm going to go ahead and confirm that that is the correct answer here, by the way. Ba-ba-dum-bum, ba-da-dum-bum, bum, bum. Oh. Still prime. Oh, yeah, okay. So this is correct. Sorry, I had a little brain fart there for a minute. So it's not getting steeper or less steep at all. However, there is one other piece of information we can tell about f prime of 1. This is either a max or a min. And the question is, which is it? Is it a maximum or a minimum? A really easy way to take a look at that is what f double prime of 1 is, which in this case is 12. If you just plug a 1 in for x in the f double prime there. Now that's positive, which means it's concave up at that point. And a graph that is concave up and is at a critical point with a horizontal tangent, this is a minimum because it's concave up, so that point has to be a minimum. The opposite would be true if it was concave down. It would have to be a maximum. Let's do the same kind of exercise with x equals 2. Kind of draw a line here. F prime of negative 2, sorry. This would be 3 times negative 2 squared plus 6 times negative 2 minus 9. That's going to shake out to be, let's see, 3 times 4 is 12. Minus 12 minus 9, which is going to be a solid minus 9. Since this answer is negative, then the graph is getting, it's getting less steep, I think is how that works. Positive numbers would be getting, decreasing. We know it's decreasing, sorry. I'm looking at these solutions on the other monitor. I guess there's more I have to say about this. I know that's decreasing, but also concavity plays into a part here. F double prime of negative 2, which in this case is going to be negative 12 plus 6, which is negative 6. So it's also concave down. So you have a graph that is concave down like this, and the point is already negative in slope. If you think about this now, not only is it negative slope, but it's going to be getting steeper. It's only going steeper and steeper as you move across this line to the right there. So this is getting more steep. This is the same question as asking you, is it speeding up or slowing down? In this case, since the first and second derivatives are both negative, it's speeding up. It's getting more steep in the negative direction. So I would say more steep in the negative direction is a good thing to write down for this answer. As far as question D goes, the values of f double prime of 1 and f double prime of negative 2 can be used to determine concavity. Where is f concave up and where is concave down? Question D we can answer relatively simply by just taking the second derivative and setting it equal to 0. This is pretty easy to do because our second derivative is just 6x plus 6, I think. I'm just going to confirm that really quick. Yeah. And that is going to be 0 when x is equal to negative 1. Just doing the algebra in my head really quick. Negative 6 over 6 be negative 1. So the thing there is that if you think about this as a sign problem, not sign S-I-N, but sign like S-I-G-N, negative 1 is where the point of inflection is going to happen. If you were to plug in a number to the left of negative 1, in for this function, it would be like negative 2, for example, would give you a negative answer. And if you were to plug in a number to the right of negative 1, like say 0, you would get a positive answer. So as far as the two points they asked us about, negative 2's over here and positive 1's over here, everything over here is concave down. And everything over here is concave up. So negative 2 is concave down and positive 1 is concave up. I realized we didn't do 5-6 part B. Let's go back to that question for a minute. Based on your sketch, give reasonable estimations for p prime of 1. Honestly, any slope between 1 and 0 works. So I'm just going to say p prime of 1 is maybe 1/2. And p prime of 5, which has got to be in here somewhere, it's got to be between the negative 5 slope and the 0 slope. So how about p prime of 5 equals, negative 3. Something like that. Just got to be in between those slopes on either side. Okay, let's keep pressing on. We are going to eventually do every problem on this except for number 11, so we have 3 more problems to do. We're already at the 24-minute mark, but I'm just going to keep pressing forward. 5-8, Lazy Lulu was examining the following limit. She recognized this is the definition of a derivative as a limit. Very powerful thing to recognize, Lazy Lulu. We're not going to need a calculator for this problem. So what you need to do here is find the equation of f, which is a really easy thing to do because it's right there in the function. If you think about your formal definition of a limit, formal definition of a derivative, it's f of x plus h minus f of x all over h. Limit as h approaches 0 there. So the f of x is that yellow part. You see x plus h, by the way. You see it right there and right there. And those are the same places that you see x in the original function. So that's another clue also for you. So the original function, f of x, in this problem is 5x squared minus 11x plus 7. And for the power rule, using that to write the derivative, it's going to be 10x minus 11, right there. That's the derivative. And as far as evaluating this limit, this is another clever question. This is asking you, this is basically asking you, what is f prime of 1? And here's how I know that. Because look, instead of x plus h, you see 1 plus h, 1 plus h. And then a good way to confirm that is to plug 1 in to the original function up here and ask yourself, do you get 1 for the answer? And that would be 5 minus 11, which is negative 6. Negative 6 plus 7 is 1. So since f of 1 equals, f of 1 equals 1, that's how I know what's going on right there. So this is asking for f prime of 1. Now we've actually plugged a number in for x, which is way easier to do by just plugging it into our derivative. That's 10 minus 11, which is negative 1. This is a good example of questions that you see on your AP test. This is all you'll be asked about the formal definition of a derivative, is to do questions like this. To be asked to realize that's just the formal definition of a derivative, using the power rule is much simpler. 5.9 is a good physics question, which we'll be talking about from time to time. Math Booster Club shot a rocket from the ground straight up into the air to celebrate Pi Day. The launcher shot the rocket with a starting velocity of 182 feet per second. Let's make a note that V0 is 182 feet per second. We're going to write a function s for the height of the rocket at time t. This question is really easy if you know a couple basic facts about physics. A of t, or the acceleration on Earth, is always negative 32. And not negative 32x or anything. It's always just negative 32. Which means that your antiderivative, if you want to go back in time and take the derivative of that, it's going to be negative 16. Let's see if I get this right here. No, it's negative 32t. But it's also a plus c, because we don't know what that constant is. And this is where the v0 comes in play, because that becomes your c. Because if you were to plug in 0 for this, because we know that v of 0 is 182. That's what the initial velocity is. So this means that v of t, in this case, is negative 32t plus 182. And at this stage, we can now do the antiderivative one more time and finally write our h of t, or our position function. Because we're basically just going to take the antiderivative of this. There is going to be a plus c, but more on that in a second. This time, you're going to have negative 16t squared. And as I mentioned in the first problem we did in this video, you'll always see, as long as we're talking about gravity on Earth, your h of t function is always going to be negative 16t squared. Your velocity function is always negative 32t, and your acceleration is always negative 32. Because of the way gravity affects Earth, it's 32 feet per second per second. But anyway, we're also going to have plus 182t. And we also need to put a plus c on this thing, but I'm just going to write it down and think about it for a moment. We know that h of 0 has to be 0, because the height of the rocket when this thing started off is 0. And it's because we know that. If I were to plug in a 0 for this thing, if I was going to figure out what h of 0 is and solve for c, I would get 0 plus 0 plus c, which is a good way of knowing that the c in this problem is actually just 0. So I'm going to go ahead and ignore it and just write down that for the final answer. That is the correct answer. Negative 16t squared plus 182t. 5.10 is the last question. We're just going to review some integral rules things. Because this video is already approaching the 30-minute mark, I do want to just run through some solutions with you. The ones that you could do without a calculator are A and C, and I think that's it right now. I suppose you could do B and E. You could do B without. I mean, these are, to be fair, these could be no calculator questions. They could be. We're going to do them with a calculator because it's just much faster, but they could be no calculator questions. So we are going to think about that. No, question D, I think we are going to need a calculator for. I'm just looking at it right now, and I don't think. Actually, we could do it by geometry, but we'll get there in just a moment. Anyway, so for question A, B, and C, we're just going to plug those right into a calculator, so I'm going to do exactly that, and that's how we're going to find those answers. It's probably worth the time on this video for a moment just for me to write down how you could do it without a calculator. So For this first one, you need to do antiderivatives, and you need x to the 5th power, and it would be a 3 in front to make that 15. That's x to the 1/3 power there, so I would need in front of it x to the 4/3 power, and I would multiply that times 3/4. Oh, my calculator's in the way. And we would evaluate this from 2 to 1. So I'm going to write that down, and now I'm actually going to use the calculator to actually tell me what the answer would have been in the first place, but that's how I would do that problem. Oh, I got to open up a calculator window too. So this is the integral from 1 to 2 of 15x to the 4th plus the cube root of x dx, which is, like I said, it's not a fun answer. It's just a weird decimal. So there it is. It's 94.139. Now, if you did that yourself and actually went through the work, it would not be a fun answer. This one I kind of withdraw on. I think this would have to be a calculator question because of the root going on in the problem. If I were to alter these numbers, I could easily make it a calculator-free question, but they didn't, so I'm not going to. Question B is going to be very similar. We can do question B without a calculator. At least we can set it up. The antiderivative here would be -4 cosine of y, evaluated from pi over 3 to 0. Actually, that's really simple. Let's do that without a calculator. Because the derivative of cosine is negative sign, so you need the negative sign there. So this is -4 cosine of pi over 3 minus, in parentheses, -4 cosine of 0. This is as far as your unit circle knowledge needs to go when it comes to doing calculus, so don't worry about that so much as long as you got it. Cosine of pi over 3 is 1/2, so this is -4 over 2. And cosine of 0 is 1, so plus 4. So that ends up being -2 plus 4, which is 2. That's the answer. Pretty easy to do without a calculator. Question C, we could also do without a calculator, but we're not going to. The antiderivative is x to the 3rd plus x. Actually, you know what? I withdraw. It's pretty easy to do with that one, so I'm going to do it without a calculator. 3 to -2. This would be 3 to the 3rd plus 3 minus -2 to the 3rd plus -2. I like that, the way it came out. That's going to be, let's see, 27 plus 3 is 30. And in this parentheses, that's -8 minus 2, which is -10. So the answer there is going to be 40. Pretty even, round number. I like that answer quite a bit. For question D, we could use a calculator for this one, but we also can just make it happen with geometry. This realizes, this question requires you to see, for question D, if you were to graph it, this is the integral from -2 to 2, but that is also the function square root of 4 minus x squared, which is going to make this semicircle happen. I don't know if I expect you to know that about that equation, but that is how it works. The graph looks like this. So the area ends up being half of a circle with a radius of 2. And the 2 and the 1/2 cancel out, so it ends up just being 2 pi. And that's the area there. So that one's pretty easy to do without a calculator. If you did it on a calculator, you get 6.28, which is double pi anyway. So that's question D. E and F are both general antiderivatives. These are indefinite integrals there. So we can do these without a calculator because there's no way to do them with a calculator. So you have to use your rules. This is -2 sine of theta minus 1 plus C. Oh, no, sorry, +2. Whoops, I withdraw. Because the derivative of sine is cosine. Opposite of what happened in question B up above. And question F, don't panic about that x squared on the bottom. This is 2x to the -2nd power dx. So the antiderivative here would be something x to the -1st, -2, plus c. That would be it. You could, I suppose, make it -2 over x. If you want it to be fancy, plus c. And we're not going to do this bottom problem with the rotating flags because I feel like this video has gone on long enough, and the first couple problems in this homework set are really bulky and also really important. So I apologize for dropping a 35-minute homework answer guide bomb on you, but this is an important assignment, and as we go forward, you're going to see more and more of these physics kind of gravity, but really that connection from position to velocity to acceleration and then back again is very, very, very central to what we're doing here in this class. So you guys are doing great. I know we're gonna be working at a very quick pace going forward, but you're just gonna do great, and you can handle it. So I will see you in the next video. Don't forget, you are awesome.